So welcome back, geometers. Today, just to kind of summarize again, we have a few things on the docket. First thing that we're going to do is we are going to finish 8.1, which is our Pythagorean theorem, which we looked at it yesterday, and I'm pretty sure we wrote the converse theorem. Love it. And then we just started looking at this. So we're going to finish this. We have a couple examples, this one included, that we'll look at now. And then we'll have some time to work through some problems using Pythagorean theorem, and then we're going to introduce something new today as well. It's all going to shove together. So checking this out. Here's a problem that I asked you guys to attempt last night. And we are hopefully going to get some time up on the boards, but we're going to try to blast through to get a little bit of catch up here. If this is x, what's this? Why? How do you know that? Well, how do you know they're congruent? Love it. I marked them both. Okay, so if that's x, that's x. Follow-up question. Can anybody tell me the angle that we're looking at here? I agree with you. Can you tell me another angle on that triangle? My gosh, how did you know that? It's good. So I know that based on that comment. If the sides are congruent, then the base angles are congruent, and the two base angles have to add up to 90. Therefore, they must be 45, I think is the logic that you're using there. Okay, so as we look at this then, I'm cool with that. Do we know this length yet? No. What do you want to call it just temporarily? We're going to use a placeholder. Everybody sees a pretty natural choice. Okay, so if we're saying find the missing side, and I know that I could have said sides, but we just said side, because I was hoping you guys would notice this. What theorem, what theorem can we apply immediately once we have a right triangle of which we know two sides? The Pythagorean theorem. Well, help me work that out. If it's a right triangle, which it is, then something squared plus something squared is something squared. What are the somethings here? X squared plus x squared equals c squared. Do we all agree with that? Easiest place to make a mistake here, but it's also really easy to fix. What's x squared plus x squared, Vincent? 2x squared. Can anybody tell me what you think the really common answer that people get goofed up with is? X to the 4 is a really common mistake. It's really common. As long as we're all aware that it is common and we look out for that, we're going to be okay. So I'm going to use Vincent's advice. X squared plus x squared is 2x squared, and that's still equal to c squared. If I'm trying to solve for c, we have a couple different approaches that we can take. Now, of these approaches, there's one that Lily, because Algebra 2, will be super comfortable with, but there's another approach that's maybe less comfortable. How much radical stuff did you guys do in Algebra 1 last year? So that's fair. I don't know exactly how I was expecting you guys to answer that, so that's my bad. Just true or false, looking at this, in Algebra 1 last year, you guys have ever seen something like this? Instead of writing square root of 27, which is not a nice number, have you ever seen it written like this instead? Other than on the calculator when you typed it in here. You guys did this in Algebra 1. How do we go from there to there? Cool. So I'm going to have you guys talk with your neighbors for like 45 seconds because somebody's going to answer that that's not learning this in Algebra 2. Stand up and move. Cool. Talk with somebody else. Like physically, everybody stand up. You're going to be wandering around awkwardly until we get an answer out of this. Sweet. I'll see you guys after this awkward break. It went really well. Okay, we have a decision to make then. I'm trying to solve for c, right? Now, the good news is that I can probably knock that out here. If I want to solve for c, what do I do? Okay, so I will take the square root of both sides of this equation. Okay, notice, really important, both sides of the whole equation. And let's look. I'll do the hard side, which I think is the right. The square root of c squared is c. I want you guys to do the easy side. What's the square root of 2x squared? I might have lied about which side was the easy side and the hard side. But with what's up here, and no offense, Carson, I like yours, but I like the work that Ashley showed just a little more. I don't think your work is really that different. except we have that middle step really clear. Can we apply the same thing that we just did there to the left side? How? One more time. So let's just check. Anybody know the square root of 2? Yeah, me neither. Okay, bummer. So I'm going to keep it in there. Anybody know the square root of x squared? Oh, so if I look at this, what's this? It's x, you guys said, so I'll take an x out. What stayed in there that I didn't have? The 2. Okay, what we have just discovered is an unbelievably convenient shortcut that is going to show up all over the place. Have you guys ever been working? Do you have friends who take pre-calc? Are you buddies with anybody that takes pre-calc? Have you ever seen them working with a really ugly circle before? Okay, if you have, the circle's really not ugly. It looks really ugly. But if you can do this, the circle's no harder than this, just so you know. We'll get to it eventually. Okay, what we just had, and Carson, you're going to help me with this because you answered this question like perfectly right away. What's this angle? Okay, 45, and what's this angle? 45 degrees. Now, we're going to summarize these here in just a minute, but I'm going to keep this statement. We're not going to write it yet, but I want to notice something. If I have a 45, 45, 90, and I know the length of a leg, what does it seem like I have to multiply to go from the leg to the hypotenuse? Like if the leg is x, I just said the hypotenuse is just x times what? Root 2. Now, we're going to see another variation of this come out with a different triangle. Here's the goofy way that I remember it, because I have trouble memorizing stuff sometimes. How many angles are different on that triangle? Like, and what I mean by that is 2 of them are 45 and 1 of them is 90. So there's only 2 different angles, right? That's what I use to remember this root 2. And we'll summarize this in a nice way here in just a minute. But 45, 45, 90, 2 angles that are the same. Root 2 is my magic number that we'll use. And we're going to do a problem like this here in just a minute. But let's kick forward a skosh. Before we move on past this, any questions about the algebra and Pythagorean theorem to take us here? Okay, I will have a nice check for that here in a minute when I ask you guys to do problems using these ideas. So if there are questions, I just want to reemphasize, now's the perfect time to ask that question. Seems like it's going to be easy. How do I go from the leg to the hypotenuse on that triangle that we just did? Wrong. Just kidding. Let me be more specific. Ashley, if I have the length x, what do I multiply it by to get to the hypotenuse? I don't think so. This hypotenuse is just this length times what? Based on what we concluded here. Not just 2. What am I multiplying x by here? It's not just 2. So let's clean this up. And I'm glad I did this. What does this say, Drew? Just this number. How do you pronounce this? Right. Her. It's just 2? The square root of 2. Now, couple ways, just so you guys know. I pretty commonly will just use the word root if it's a square root. There might be other ones that exist. I know Miss Sweet does not prefer the word root. She prefers rad, I believe. Root 2 works fine for me. Rad 2 works fine for me. Or if you want to be really formal, you can say the square root of 2. Any 3 of those I'm okay with. We just multiply by root 2. Now, that's to go from here to here, right? What if I want to go the other way? Instead of multiplying by root 2, what could I do? We could divide by root 2. At which point, just thumbs up or down. In algebra, I learned how to divide by the square root of a number. I have no idea. You guys don't seem to have much of an idea either, to be honest. Definitely the multiplying stuff you saw. The division, maybe. I'd have to look, or I'll have to go ask Russell, apparently. Okay. 45, 45, 90s are kind of nice. They're special triangles, right? Is there another special triangle that shows up other than 45, 45, 90s? I'm not even thinking, like, that's just an isosceles triangle. Are there other nice triangles that show up? So 30, 60, 90s, we'll definitely get there. What about in the general world of triangles? We have scalene triangles are all different, and we have a whole bunch of different classifications. But isosceles were nice. Is there an isosceles that has all three sides the same? And we don't call it isosceles anymore. It has its own special name. Equilateral. Can we all agree that equilaterals are a nice triangle, quote unquote? What's nice about equilaterals? They're all the same. When you say they're all the same, let's expand on that. What do you mean they're all the same? What's all of them? What are they, I guess? So all the angles are the same. I love it. So if we have this, I'm going to sketch it nicely here. I think that every single one of these angles is 60 degrees. And Carson, I agree with you. Love it. I'm not going to write the 60 up here. I lied. I'm going to do it like this, though. 60 degrees for the big angle. Now, if I wanted to somehow get a right triangle out of this, that's the goal. Can I add a special segment to this triangle to get a right triangle? Maybe two right triangles out of it. A bisector. I love that word. What do you want me to bisect? Okay. Carson suggests that if we wanted to add a line, we could do this. Now, there's a couple things that we have to really be careful about. When you said bisector, I love it. What's being bisected here? So what do you mean the triangle is being bisected? Do we make two similar triangles? Could you convince me that we make two similar triangles? Okay, convince me that these are two similar triangles then. So this has a 60 degree and this has a 60 degree. Where's the other angle? So there's a way that we can cut this that guarantees it's 30-30. We can bisect an angle, and that can happen. Now, here's the cool part. Because when you just said bisect, I didn't really know what you meant. And what I interpreted that as is not that we're bisecting the angle, but I interpreted that we bisected that, is how I interpreted that. But it's the same thing, right? Like we get both of them. If I do this and I draw the perpendicular bisector, we get angle, angle. If I view this instead of drawing the angle bisector, then each of these would be 30 degrees, and we would again use angle, angle. You were right on both ways without being specific, which is an awesome coincidence. Okay, we do indeed have two congruent triangles, or sorry, they are congruent here by happenstance, but they're also similar. I prefer congruent for this, but that's okay. Anything else special about these triangles, like the big 60-60-60 triangle we started with? All the angles are the same. All the sides are the same. Now, this is going to feel bizarre when I do it. I want to say that this side is 2x. What's this side? And this whole side is what? You're right, and I'm not going to write it, though. You are correct. What's just this part? 1x. How'd you know that, Carson? You're killing it today, by the way. Because we bisected, right? We have two similar triangles or congruent triangles. We know that that must have been the midpoint, and it works out. Okay. Lily, you were right, just so you know. And I think that you guys might have glanced a little bit at these yesterday, briefly, maybe. Yeah. Okay. So check it out. I only wanted the 60-60-60 up here because it's so stinking nice. What kind of triangle did we really boil this down to? It's two triangles now. What's 60, 90, and what's this one? 30. So check it out. We are going to use the values that we have, and I'm just going to say, I'm going to work downward so we can see both of them at the same time. And I just want one of these, one of the 30, 60, I'm going to use this so it doesn't look like minus on mine, 60, 90 triangles. Are we taking the left triangle or the right triangle to think about this? Okay, let's take the right triangle. So we're going to take this one, and all I'm doing is I'm going to draw just that triangle so that everything else doesn't confuse me. So here it is, and it's a right angle. And Vincent, can you remind me what's this length that was on our big triangle that we just took this out of? 2x. Love it. Andrew, what's this angle from the big triangle that we just took out? Love it. Raylene, this angle was a what angle up top? Love it. Camille, this bottom length was what? X. How many of the sides of this do we know right now? Could we find the third. Now, for this, I want you to do that up on the board. Cool. Yeah, we're going to go work this one up on the board. Take your notes with it. I'm going to pause this really quick just for some editing. Your job, I'm going to call it right now. What do you want me to call this for an unknown? A. Deal. I'm going to call that A. At your boards, I want you guys to solve A, or for side A of this triangle for me. Looking at this, I want us to make real useful sense of what's happening here. These, would you agree, are two special triangles? What's special about the first one? It's a special right triangle even. The first one we did, what was special about this triangle? And if two of the angles or two of the sides are the same, it's an isosceles right triangle, which is special. This one is also special, but it doesn't have a nice specific name other than a 30, 60, 90, which turns out to be crazy helpful. When I look up at the board, what I see is I get X. And what was the other part of it? Root 3. So what we have just done is we have done the, I would say, the generalized example of some really handy shortcuts that we need. Okay, we are going to summarize these with a nice picture. I know that sometimes people like the really wordy versions of stuff. We're not going to use the super wordy versions of stuff. Not for this. Okay, as we're looking at these, we are going to sneak this in. I'm trying to recall if these were theorems or if they were just, I assume they're theorems. I would almost bet money that they're theorems. I just don't recall. Are we going? Yep. Sweet. So we did 8.1 and 8.2. That was the converse and the Pythagorean theorem. We just wrote it as one. And then here, we are going to knock out 8.3 and 8.4 right here. So these theorems, they're going to be 8.3 and 8.4, but we're going to see if we can't make this a nice singular statement. So we'll just call this special right triangles. Okay, of these special right triangles, there's two flavors that we get to deal with, and we just dealt with both of them. The first one, it was an isosceles right triangle, and what were the angles? So here we go. Our first special right triangle is a 45, 45, 90, and I'm going to put degrees on each of these. This is a special triangle, and we've already done the generalized version, which is going to make this way faster. If you guys can still see it on your board, or on your notes, I'm sorry, we're going to use pretty much the same thing. On this, and I'm going to orient this just a little bit differently for no particular reason, is this a 45, 45, 90 if I mark those? Okay. Now, I don't really care if we use X or Z or Y. It's irrelevant to me. X is the most natural choice. Do you agree that these are the legs? Leg and leg. And what do we call the third side? The hypotenuse. I am not going to write the word hypotenuse every time. I think we should just all commit to hype. Let's get hyped. Let's go. All right, cool. So as we're looking at this, if I give you any leg length, say it's X, what else do I get essentially for free if we just look up the general example that we did above? I know the other leg is what? X. So I can write that. Don't really need it because they're both going to be there. What if I want the hypotenuse and I have a leg? What did we write above? Two of the angles are the same. What do we multiply to go from leg to height? Look at your notes. The last A example that we did. Lily had it. One more time. X, and we simply multiply by root 2. Now, for this, you guys are going to demonstrate your ability to do this. I'm trying to go pretty quick today because I want to get a little bit caught up from or to fifth hour. Did we go over our tests in here? Okay, so that explains why we're a little bit off kilter here. Okay, for this, if you want it, completely optional. But if you think you might look at this and go, oh man, I can see it, but I don't really know how to use this, I'm going to make sure that we can see this. If I want to go from a leg to the hypotenuse in a 45, 45, 90, we multiply by what? So careful. Do we multiply? So let me think of how I want to word this. because you're right, we do multiply the length x by root 2. But if I already know that this is x, all I have to do is multiply it by what? Good. And I think that it might just be a way we were wording it, or the way that I worded it. I multiply a leg by root 2 and I get to the hypotenuse. On what kind of triangle? Try it again. 45, 45, 90. We just take the leg and we multiply it by root 2. Okay. I have no issue if your answers have root 2 in them. I actually prefer it because the square root of 2 is like 1.414, blah, 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 blah. I like root 2. I'm okay with that. Okay. I want you guys, and I want to see if we can sort this out. What's the other special triangle that we dealt with? 30, 60, 90. So 30 degrees, 60 degrees, 90 degrees. Now, we used the right triangle, I think. I'm going to draw it with the left one, but I'm going to make one claim about this first. I only had to use leg and leg here. If this is a 30, 60, 90, and would this be the 60 or the 30 right here, this bottom angle? Why? I agree. So you were thinking up from the picture above, which is completely valid. The triangle, not the triangle inequality, which is something that we talked about. We had to brush through this at the end of the semester, I'm pretty sure. So it was really quick. The longest side is always opposite from which angle? The 90. So the shortest side should always be opposite from which angle, do you think? Biggest side opposite from biggest angle. That's what we just said, essentially. So the smallest side, where do you think it should be opposite from? The smallest side or smallest angle. Yeah, I would agree with that. I look at this. Do we all agree that this is a short leg? Okay. Here's the part where if you're zoning out, I need you to stop. We, instead of just writing leg and leg, I'm going to actually use short leg. Now, I don't care whether you think of, when I just say imagine royalty, real quickly, in your head, I want you to imagine royalty, a royal person. Does everybody, if you can imagine pictures in your head, do you have a person in mind? Tell me about your person. White hair, so they're old, okay? They're probably dressed fancy. Is it a man or a woman? Good on you guys. I heard both. I don't care. Call this king, call it queen. I don't care. Either one's fine. I'm going to make a claim. This is the most important leg of our 30, 60, 90 triangle. This is our queen. Since we've been in chess mode, this is the most important leg of this triangle. So check it out real quickly. Which leg on a 30, 60, 90 is the most important? The short leg, and here's why. Based on the example that we did above, and I should have done a concrete example, but I was just so excited for the theorems. If I want to go from the short leg to the hypotenuse, all I have to do is multiply it by something. Look at B that we worked just a second ago. It's not on the screen right now. Oh, you guys already have it. To get from the short leg, and did we write it? Did you guys write this in your notes also? To get from the short leg to the hypotenuse. Is this the hypotenuse? So if this is my short leg, what do I multiply this by to get here? 2, right? So if this is x, this must be 2x. What do I multiply the short leg by to get over here to my long leg? Root 3. So it's x, whatever that is, and we just multiply it by root 3. Now, the reason that I say that the short leg is the most important, and that's subjective. There's no real most important side of a triangle, except for the fact that if I know the short leg, I can immediately and quickly get to both of the other sides of my right triangle. If I have the long leg, I can still get to the others, but it takes a little bit more work. Do you want to have the similar statement like this, just so we can see how it works? Okay, so check it out. On this one, we're going to stick with green. If we're not going to do every combination of these, just so you know. If I want to go from the short leg, and I want to wind up at the hypotenuse, what do we multiply by? So times 2. Now, these ones, I want it to make very clear times 2, not 0.2. What if I want to go from the short leg to the long leg? I multiply it by something. Root 3. Now, the way that I remember this in my head is 45, 45, 90s have two angles that are different. Root 2 shows up in a 45, 45, 90. How many angles are different on that 30, 60, 90 triangle? And what shows up in our shortcuts here? Root 3. And that's how I keep this straight in my head. Now, we didn't write the other side of the statement over here. What if I wanted to go hypothetically from the hypotenuse to the short leg? Divide by 2. We're just going the opposite direction. We're doing the opposite operation. Love that. Nice job. Divide by 2, and we get the short leg. There's one uglier one that we have to address, I think. What's the other one? Ooh, the long to short. And this, similarly, we did not write this out on this one. We never wrote the hypotenuse to the leg on our first one. We might go back and do that. Well, Vincent, if I multiply by root 3 to go from short to long, what if we go the other direction? Squaring, it's not a terrible idea, but I think there's an easier thing. I'm going to word this differently. I'm trying to think of how I want to word this differently. I was so excited about it. We multiplied to go that way, right? What's the opposite of multiplication? Divide. If we took the square root of this, it would not take me to x right now. But if I divided by root 3, would it get me to just x? If I had x times root 3 divided by root 3, does anything fall out of that? Like those are gone, right? Because that's just a what number did I just cross out? 1. Root 3 over root 3 is just some choice of 1. So check it out. We would just simply divide by what number again if I wanted to go long to short? Root 3. What about on this one? We've taken a minute or two break on it. What if I wanted to go from the hypotenuse to a leg here? Divide by 2? Root 2. Now, there is some algebra that's going to be ugly with this that we're going to cover on. Okay. This is taking longer than I thought. We might not get to start at the next section, but we're going to try. For this, there's one more thing that I know Miss Sweet talked about with half of you guys yesterday. I'm Kyle Holloway. My wife is Leticia, and together we have a child. Now, get some qualities from me and her, right? So since Zeke is my kid, me and Mrs. Holloway are the parents. Can we all agree with that? Now, yesterday, you guys in the middle, and I want to see if it's still up here. Can you walk me through what's happening here? Somebody that was working this, because I love it, but our group yesterday didn't quite discuss this. What do we see happening here? Three, 4, 5. Ooh, a Pythagorean triple. Now, half of you guys did not see that yesterday. Nice job remembering this, by the way. You're killing it today, man. Anything special about 3, 4, 5 with regard to right triangles and the Pythagorean theorem, maybe? Okay. Ooh, they're all what? Whole numbers. They are whole numbers. But I don't think that that's quite what I'm looking for. I want you guys to try something for me. There's not many times that I say you have to do mental math, but we're going to do some mental math together. What's 3 squared? So I'm going to write this over here just so we can see it. Can everybody see the 3, 4, 5 written on the middle board? 3 squared is 9. Plus, what's 4 squared? What's 5 squared? Is this true? 9 plus 16 is 25. And if this is true, these must be the somethings of a right triangle. But you think they're the angles? We have a 3 degree, 4 degree, 5 degree right triangle? The lengths of the sides. That's what we're always checking with Pythagorean theorem, right? So for these, we're going to go super quick with these. And I'm going to give you just a couple. We're going to define real quick Pythagorean triples. Now, there are a lot of ways that people can write these. I'm going to stick by a single convention for these. And if you have a slight alternative, as long as you know what you're doing, I'm cool with it. But a Pythagorean triple. all that we need, I'm going to keep these in order as best I can, but these are just three sides that satisfy the Pythagorean theorem. Like a triangle with these side lengths that we're about to write, where the Pythagorean theorem works. So if I want to be a little bit more specific, I can define it a little bit differently. I write them as ordered triples, which I don't think you guys have ever used. What's an ordered pair? Can you give me an example of what an ordered pair looks like? X, Y, X comma Y, right, with parentheses. Now, whether you use the parentheses, I like to because I confuse myself if I don't have it. We're going to say that these are the lengths A, B, and C of right triangles. Now, the cool part about this is that when I asked the question about me being a parent and Zeke being my child, Ashley looked at me like I was crazy and thought, where the hell are we in geometry that we're talking about you having children? Which is fair thought, and I don't really know if that's what you think. That's what I heard, but like signals get weak on Fridays. The lengths, no, okay. The lengths of A, B, and C in a right triangle. Another way to say this is if it's A, B, and C in a right triangle, what theorem is going to be held to? Hence the name. Now, I write them as ordered triples of the following form. I write mine when I do it, and we'll just do an e.g. 3, not 3, weird. A, comma, B, comma, C. Where by default, what is C on the Pythagorean theorem? So I'm just going to highlight that is the hypotenuse. Okay. As we're looking at stuff, that went right in her bag instead of hitting her. That was not a good throw. Jody, will you nudge her? I need you to do me a favor. I threw a marker at you, but it landed in your backpack. Will you grab it for me and toss it back? Like, for real, there's a marker in your backpack that when you get it, just toss it up to my hand. It's just waiting. Okay, when we write these, what I call, and the reason we're talking about the parent part of this, is we have some that are really nice and some that are offspring, essentially. So we're going to get a few of the parents, and we'll see, because my memory is bad with these. And I'm going to move over here, but I'm going to do the same thing. Parents. And I'll even say parent triples. Can you guys give me any Pythagorean theorem that you guarantee there's a right triangle with these three sides that works? 3, 4, 5. So check it out. 3, 4, 5. I'm going to keep consistent. Red is our parent. 3, 4, 5. Okay. This is a parent triple. I'm going to make a claim. If I have a 3, 4, 5 triangle that I've dilated, is it still a right triangle? For sure. If I dilate, it's similar, right? It's a similarity transformation. What if I dilated it by a factor of 2? Does it get bigger or smaller? So I could enlarge it by a factor of 2. What would the new lengths be? 6, 8, 10. Do you guys agree that this is a dilation by a factor of 2? We're going to go a step further. Check it. What's 6 squared? What's 8 squared? If I do 6 squared plus 8 squared, I get 100. What's 10 squared? Oh my gosh. Here's the parent. What do you think I'm going to call this one? It's a child. It's like this Pythagorean triple has infinitely many children. We just did it by a factor of 2. We scaled it up. I don't want to, but could I do it by a factor of 7.1? As long as everything gets proportionally larger, I'm going to have similar. I'll still have a right triangle. It'll still work. So I love that you bring that up. Yes. Can you guys give me 2 more children real quick? Nice children if you can. Well behaved, easy to deal with. 12, 16, 20 is one. I think you skipped one that I would write. Give me another one, not Carson. Can you guys tell me how we got 12, 16, 20 to be this? Yeah. Now, what I would encourage is if you get 3 sides of a right triangle, if you look at it and go, well, it kind of looks familiar, could I factor a 4 out and just say it's a dilation of 4 of this? And then we would recognize it. Is there another one in between these? Here's a double, here's a quadruple. Which one did you skip? So 9, 12, 15. This is just times 3 to get here. Infinitely many. We don't have time to write them all. Can you tell me yours again? Because I was not ready for that one. We're going to fact check this. What's 9 squared? 81. What's 40 squared? Pause. What's 4 squared? Now add 2 zeros. 1600. Now, I have a sneaking suspicion that the square root of 1681 is going to be what number? 41. I'm just going to check real quick. 41 squared. It is 1681. Holy cow. Carson, I am as sincere as you can imagine. I did not know this one. I know 3 parents off the top of my head. Awesome job. Does this one have children? Give me one child of this one. I'm not going to write more children, but there's infinitely many of them. ... Anybody have another one off the top of your head that you know works? Ooh, I have one. What if I say one side is x, I'm going to leave this one blank, and this one's 2x? Just x? X root, huh. What is this, the parent triple for? What sort of triangle did this come from? Kind of an equilateral. We cut it in half. A 30, 60, 90. Okay. Is there another one that we have from another special right triangle? XX and x root 2. And this would work for any x. I could do 5, 5, and 5 root 2, or 10, 10, and 10 root 2. They would all work for any x value. Now, these ones, they will show back up. We have a parent here, a parent here, a parent here, and a parent here. There's 2 more that I have ready to lock in. These, I want to be really specific. They're optional. These are shortcuts. If you don't remember your Pythagorean triples, the worst case scenario is you have to do a Pythagorean theorem. This is a time saver. It's worth knowing, but it's not going to make or break your ability to solve these problems. Okay, I want you guys to give me the third side. I have one more locked and loaded. 512 something. Talk with your neighbors, get me this parent, and I'm going to put a star next to every parent rather than the arrow because I like that more. 512 something, and the other one is 724 something. I hope. We'll find out if it's not. Oh. Let's see. 25 plus 144 is 160. Yeah. Five squared plus 12 squared winds up being 169. And you guys might not know this one. What's the square root of 169? And if you didn't know it, it's here. Hopefully now you do. Okay, and all the children. I think this one also works. Miss Sweet, you're more than welcome to correct me if I have it. Okay. I only remember a few of them. Let's see. 7 squared. I'm just going to give you this one. Pretty sure it's 25. Okay. 2 interesting things for you. Or I guess one interesting thing and one thing that you'll like even more. First thing. Just with your gut. Are there infinitely many parents? Or do you think eventually we reach a point where we've used all the parents and everything else is just children? You think that we're eventually going to run out of them? Anybody else have an opinion? Okay. I'm not going to tell you if you're right or wrong. I just like the idea. Thank you for sharing. Okay. As we're looking at these, that thing I thought you guys didn't really think necessarily that you'd like it. I'm going to hook you up with something to do because I hate the thought of you being bored over break. Don't worry, I got you. You get an unreasonably long amount of time to work through this. I want homework 8.1, page 355. And you get the privilege of working problems 4 through 7, and 15, and 16, and 20, and 21. Okay. I will try my very best to remember what I was going to say at this point, apparently, because I don't know where that was going. So scratch that. First day back from break. We'll take this. Oh yeah, if I don't upload the answers online, please let me know. I'm going to, like, it takes me a few minutes to do it because it's a pain in the butt on my end. Please email me if you see that they're not there and you guys like to check your answers. Cool.